how do you do your job? And how do you think like a programmer? And we're going to start with that, actually with how a computer thinks, because the two are interrelated really, really well. So again, questions at the end, although if there's something I specifically say you didn't even hear the word, say I'm sorry I didn't get that, okay? Because probably that won't pick it up either. Okay, good. So the basic idea of how a computer works and thinks. The biggest thing to think with in terms of computers is that there is no gray area with computers. They can't think with almost or maybe. They just simply think with yes or no, 1 or 0, on or off, 5 volts or 0 volts. That's the only way they can think. And it isn't how we think. When we think in differences, similarities, and identities. That's how we think. You look at an orange and you go, oh, well, that's similar to a lemon, but I've tasted them both, and there are differences, right? You look at 2 bowling balls and you're like, wow, there's that incredible amount of similarity, but they're not exactly the same thing. You look at twins, and like, wow, there's an identity there. And yet you can split it apart and say, they're not exactly the same thing. We can think of those kind of things. Computers can't. They just simply think, is it on or is it off? Is it there or is it not there, right? So how does a computer think? This think thing comes up a lot, and the media just kind of has a field day with computers thinking. They only do what we tell them to. And I know that a lot of what I'm going to go over here you guys kind of know, but I just want to put it all together in one communication. So the way the computer thinks is just simply tell them what to do. And that's all. That's all it does. You just tell them what to do. I'll do it. Move to the right. Okay, good. Now what? That's all it does. It's your slave. Gabe Newell in that video, the code video. Gabe Newell, he's the founder of Valve, big computer game company, right? He called a computer possibly the stupidest device ever created, something along those lines, right? And he's right, because it just simply does what you tell it to. So we're going to go all the way down inside this thing called a CPU. So people made the CPU, the central processing unit, right? Made this machine that has some sort of a control part, and it has a big old storage area where you can put data into it, and then it has a way to get data into the machine and a way to put data out from the machine. Well, it's still just a machine. It's not going to do anything, right? So if you want to think of like, how does a computer work? How does a computer think? Even when you do these high-level languages and these complicated programs that you're writing, at the end of the day, one step at a time, you're putting data into the machine, telling it to do something. The thing that it needs to do may need to access some of the data that it has internally. It could have it inside a hard disk drive, it could have it inside its own memory, which is RAM, but either way, it's still just saying, I need some data to operate. And even those things are done one step at a time of find out where to get the data, find that location good, get the value that's in there, do something with it, send the result out, one single step at a time. So when you are writing a computer program, if you think the same way with one thing at a time, you'll do well. One of the challenges is that the software development field has gotten up to the point of complexity and skill of its practitioners that they like to take shortcuts. And to give you an example, at this point in your education, I think a lot of you have seen in coding. It has to do with a very fundamental concept, that of dealing with variables. Remember this storage area over here? We'll actually keep that. And we're going to be talking about RAM, random access memory. The first thing you need to do is just segment off a certain portion of that you're going to use for a specialized purpose. It's going to store data. That's done with declaring the variable, right? So you can declare a variable and call it Elmo. There. What that does is set off on a reserved portion of the memory. There's nothing in it yet. It has no value. Then you can say that Elmo is assigned, there's the assignment operator, the value cheese. Okay? At that point, now you actually put a bunch of ones and zeros in there that make it equal to cheese. How often do you see it written that way? Not very often at all. What do you see? Var Elmo equals cheese. A couple of you have bumped into this along the way. I remember having conversations with you about it. It's shorthand. It's a shortcut. It makes your job easier. But if you don't know that there are two separate things happening, it can get quite confusing. On the other hand, if you know how this machine that we just wrote up here works, that it does only one thing at a time, then you'd be able to figure out that there are two things happening here. If you know that the only thing you can do at first is reserve a piece of memory, well, that's got to be in here somewhere, and that only then can actually put data into that memory, well, then you know there's a second thing going on here. At the beginning, when you're writing code, I highly recommend splitting it out. Only when you personally are comfortable with combining things, because you've really got it down, put them together. And in fact, there's nothing wrong with always writing your code like that. Even as an experienced developer, when I go through and I read someone's code that's like that, it's a joy. I don't have to spend all that time figuring out kind of, oh, what did he combine and make into one shorthand version, but it does all the same things in 7 different steps. That's awesome. That's great. I'm very impressed. But it's a lot easier to take over someone's code base when they don't do that. So that's a little bit about like how a computer thinks and how the way you write your code fits in with the way the computer thinks. Again, much of this you've probably gone over a little bit, but it's leading to how do you think as a developer, right? So the next subject that kind of falls in line with here is this whole subject of flowcharts. How many of you before this had ever encountered a flowchart or knew of the concept? Okay, all right, good, a couple of you. So here's the thing is that we've all encountered a flowchart before, but not known that it's a flowchart because it's not really drawn out the same way. But a recipe can be a bit of a flowchart. The instructions to operate a lawnmower, it's a lawnmower, can also be thought of as a flowchart, but usually they give them to you verbally. Well, what you got to do is you got to push on there, preload with a little bit of gas, and then you got to check in and make sure that you got oil in there, and then you go and hold the handle down so that it doesn't kill the motor, and then you reach down and you give it a real quick yank, and if it doesn't start, then you let go and start the whole thing over again. You're giving those instructions verbally, but it's a flowchart. It's just about if, then, these decisions that need to be made, right? So what it does is give us a common framework to think with in terms of illustrating how a process is going to occur. And it so closely parallels how you have to make the computer operate that is a very, very valuable thing to learn. But it also is how computers think. And it is therefore how you'll think as a software developer. So I'm not going to get into a bunch of specifics about the individual elements of it. Okay, you've seen some where this is a decision, you're going to go yes over here, or you're going to go no over there, right? And then there's operations that can be done. This means some work got done, and that sort of thing. All the symbols are in the book. You can look at them. But the point is, you start here, and you go through. You can have branches of execution. You can have decisions that need to be made, and based on that, you can go to different paths and routes. This is how the computer has to think, because it can never have a not sure or an undefined way to behave. They cannot work that way. You and I can. We can, to illustrate, about 20 years ago I had a job where I had to fly to Australia. And I had to be dropped off with a bunch of equipment to set up a sunglass stand out on the roadside. I didn't know anybody. I didn't know how to operate in Australia. I knew how to sell sunglasses, and I knew my stuff was probably there. That's all. How do you write a program for that? How do you write an exact plan of execution? You don't. You figure it out as you go along, right? Computers can't do that. Unless it was an incredibly well-detailed flowchart that kept track of every single possibility, decisions to be made, then the computer program would probably have a chance of doing it. So if you learn flowcharting and how to actually map out the different paths of execution and the different choices that need to be made, you can write a competent computer program. And more importantly, you can debug why a program that you didn't write isn't working well. Or you can dive in and figure out, it's working great, but I need to add on new functionality. Where do I cut in to add in new functionality? Does that make sense? Okay, good. So, flowcharts. Learn those little symbols. There's only about 5 or 6 of them that you use commonly. And become very comfortable with them. This will help you really start to think the way computers think, and with the way, as a software developer, you need to think. The biggest point is, you have to tell the computer what to do at every turn. And it will do nothing unless you tell it to do so. Right? Alright, so now, a whole subject of problem solving. There's a couple of different aspects of problem solving that I want to go into. The first one is just a general approach to isolating a problem with a system. This goes back to my electronics technician days in the Navy. They taught us a concept called half splitting. If you have an overall system, and the system is composed of many different parts that are all interconnected, and somewhere along that chain of execution, a problem is happening, and you don't know where it happens, then find a way to isolate one half of the system, test only that first part, and if you find the problems in there, you can completely eliminate that entire sector as having a possibility of having the issue. It's logical thought. Totally got it. Many of you will probably go, well, duh, Eric. Not everybody thinks that way. And they'll just guess. They'll guess at where they think the problem is. The trouble with guesswork is you're right often enough to think that it might be a valuable way to approach things. It's not. It's absolutely not. And as you get into very, very large, complicated systems that have lots of interrelationships, it's an atrocious way to do business, and you'll spend a lot of time beating yourself up. Always find a way to isolate one part of your system as having any effect on whether or not the problem will be replicated. That's called half splitting. Same thing, by the way. If it turns out the problem wasn't over here, well, you know it's somewhere in this side. Fine, cut that in half and test one. Oh, it's not there? It's got to be in this final quarter of the system. Now you're starting to narrow in on it. Does that make sense? Mm-hmm. This is the approach to being able to isolate how any system works. And it isn't just for troubleshooting. It also completely works if you're given a brand new system and you're not sure how it works. Fine. Go just somewhere in the middle of this thing, like you have we're doing an exercise, some of us right now, where we're building a script that can go check a file folder for the files in it, see if any of them have been edited within the last 24 hours, and if they have, copy them over to another folder on a different machine so they can be taken, because those are new or edited or updated files, right? If you weren't sure exactly how it was doing its job, it would be real easy to put a stop right before the files actually arrive at the destination folder and see what arrives. And if what arrives seems to be improperly formatted files or not correct, then you go earlier in the chain of execution, find out where you are getting the expected result, and now you've actually got what to work with. Like, why is it messed up? This is the way to think with it, right? Or, if it's completely working, that's fine. Choose a point that seems to be halfway through the execution. Oh, okay, I should be getting a set of files here. Oh, I am, good. Well, how are they formatted? Not quite sure how that works. Step back one portion earlier. Oh, okay, I see. But now you're just dividing it into chunks, into sections. Good. So, this whole area of problem solving and that process I just talked about leads me to one of the main things I want to discuss today, which is how to handle frustrations as a software developer. And there's something that's even senior to anything I've talked about here so far, which is that there is absolutely no way on God's green earth to be able to teach anyone everything about software development at all. There's actually not even a way to teach anything, a single person, everything about a specific language. I'll give you C# as an example. C#, which comes from Microsoft, and it's part of that whole .NET tool set, those tools for making software programs. The full documentation on it is about 1,600 pages long. It's tremendous. And there's no essays in that documentation about how to use the language. There's just simply, here's how some of the commands work and how to actually use them syntax-wise. And this is what the command will give you if you use it over and over and over and over and over and over for 1,600 pages. It's an incredibly large body of work. It can allow you to create thousands of different types of programs, and you're never going to learn all of it. I don't know all of it. I make a great living working in the C# arena. I don't even come close to knowing all of it. In fact, here's the point. As an experienced software developer, whenever I encounter a new project, I am familiar with usually about 15 to 20% of the technology that's going to be used on that project. The rest of it, 75, 80, 85%, I'm not sure what it is or how it works. I'm not sure. It's happening right now on the project I'm on. Every single other person on that project is in the exact same boat. But what we all have in common, besides a lack of knowledge of how those specific technologies work, is the know-how how to figure it out. And that's actually senior to everything. In fact, there's something I want to say about how the education in the school is structured and any effective education, particularly in a complex area. The ultimate goal to be an expert practitioner in the area is to be able to have the know-how of figuring it out as you go along. But you can't do that effectively if you don't know the bedrock fundamentals of how that area works. So we're trying to do two things here. We're trying to give you the bedrock fundamentals of how computers and software work within the framework of 1 or 2 or 3 languages. But more importantly, and that's what this talk is about, and a training focus from here on forward, what this is about is teaching you how to figure it out on your own. The correct mental approach to doing so. And not just the plain old, pragmatic things of where are the best resources online, but how do you do it? How do you figure this stuff out, right? So I'm going to give you some of that today, and we're going to continue to emphasize that, because that's actually the most important thing to walk out of here with is, okay, so I know some of the syntaxes of these different languages, and I know what a method is, and I know it has a signature, I know what variables are, I know how I can control if, then, else, I can iterate through a list of things. Okay, got it, great. Now I get a real programming assignment. How do I start? How do I think with this thing? That's actually much more important, and that's what we're going to be putting some effort into, okay? But the big point about that is that happens to everyone, not just a junior developer. That happens to me every day on the job. And the guys I work with, we're senior guys, every day we encounter something we're like, I'm not quite sure where to start with this. All right, better dig in. And we fall back on a certain methodology of thinking in how to approach it. And that's what I'm going to try to impart, is that methodology of thinking. So here's how that thinking works. You fall back on the core elements of a program. A program will do some very common things. It'll always declare some variables that it needs. It'll always have some logic that involves input and output, and it'll always end. It'll always do those things. Okay, good. All right. And it'll also always obey a flowchart. It always will obey a flowchart. Okay. So let's say you've been given a task to figure out a program. Start with knowing that you're actually going to have one central framework where you're going to declare some variables. It'll have some logic that accomplishes what you want to do, and this logic is how to implement the flowchart, and you'll end the program. And then start to build tiny chunks of this overall thing. One of the mistakes I see developers do is bite off the whole thing. It's really, there are guys that can do it. There's some guys in this industry that are mind-bogglingly, insanely intelligent. And they can comprehend an entire huge program in their head and just start writing the whole thing. It's not me. And I'm successful in the industry. It's not me. What works for me, and what I see work more commonly for people, is just simply figure out, okay, so I know that if I'm going to start at point A and eventually arrive at point B, along the way there's decisions to be made, there's things to be done. Let me just start writing one of those. And it goes back to this concept of half splitting that I talked about earlier. Splitting into these manageable chunks, you're isolating what you're working on from outside influences. So you'd start with, as an example, this is for some of the guys in the room who I already worked with on this project. If you're given a task where you need to find a folder in a file structure and locate all the files in there, and then check whether or not they've been modified or created in the last 24 hours, start with locate the folder. Let's just do that. Let's not build everything and, okay, let's immediately write the code that finds the files, checks whether they're less than 24 years old, and then copies them over into a destination folder. No. Let's actually just do that one thing. And once we know that that works, and it's beautiful to write it because you're controlling every aspect of how it is. It's not dependent upon, oh, well, how do we start the program? It's not dependent upon what are we going to do with the output of these folders. It's not dependent upon where are we going to copy it, how are we going to copy it. You don't care about any of that. You're just solving this one little problem at a time. Isolate what you're trying to solve into tiny chunks. Never try to solve the whole thing at once. Okay? So once you've got this working in your little self-created universe, then you can go on to the next thing. Okay, good. What's the next thing? List all of the files in that folder. Oh, okay, good, awesome. And only build that. Just build that. And then after that, check their age. Okay, good. Just build something that will check the age of a file. Just check the age of a file. Then give it the list of all the files you made. But notice I broke it up into two tiny little chunks. Don't try to implement, oh, I've got this great big list of files. Now I've got to figure out a way to give the whole list and check all of the files in it for whether or not they're less than 24 hours old. No. Just prove to yourself that you can take a file and check whether it's 24 hours old or not. Just do that. After that, add the complexity of giving it the entire list, iterating through the list, checking along the way. You see these little bite-sized portions that you're building with. This isn't just a smart way to build something, it's actually how the computer thinks. It can only ever do these one thing at a time. So if you start building it from the one operation at a time, and then add the complexity of doing several at once, which isn't at once, it's still this, and then this, and then this. If you can do that, you'll be able to develop a large program. And you'll also be able to do the reverse, which is you'll be able to get a large program you've been given and start to dig into it to really, really think. For example, very often in programs, you're going to be dealing with objects called dictionaries. Who here has heard of a dictionary object so far? Okay, good. So dictionaries are really valuable, and there's lots of different kinds, but essentially, all a dictionary is a list. It's like kind of a complex, slightly complex list. It's just that you have a key and a value for that key. What does that mean? You got a key called name. And depending upon the content of the dictionary, the value of it could be Dave. You could have a key called age. Its value could be 27. Make sense? Okay, there's lots and lots of ways you can actually make this very complex, very useful, but essentially you've got this dictionary of keys, values. These are called a key-value pair. Good. So, when you have dictionaries, often you're actually going to have to do stuff where you need to go from the top of the dictionary and all of its entries all the way down and do something to each entry, or you're going to have to find a specific entry in it, or you're going to have to add another entry to it, or you're going to have to delete an entry from it. Make sense? It's fine. I'm sure you can think of common things you want to do. If you have a roster of students and their grades in a classroom, that would be a thing that would happen all the time. So if you really want to dig into the logic, remember you declare your variables, and then you have that logic, and then you end your program. If you want to start digging into how does this work because you got given a program, find where it makes these dictionaries, because that declares your variable, and then find where is that dictionary operated on? Where is it used? So I declared a variable. When does it first get used? Now, luckily, a lot of the software development tools we have available nowadays make it easy to do that, even for a very, very large program. You can literally search for if this is called a student list. You can search your student list, find it in the code, and go, oh, here's the 5 or 6 places that it's being used. Put a breakpoint on each of them. Make the computer stop where you want it to. Hit run. The first time it hits that dictionary being used, you're right there, and you can watch. Typically, it'll be when it's populated, because you have to have entries in the dictionary before you can do anything with them, and you can watch the program populate the dictionary. So even if you've never used if you've never been a business user for the program you're being asked to maintain, you can still start to get a sense of what it's going to be like for them. By the way, this is an aside. This is all inside the code, and your ability to intuit and figure out and research how this program does what it does. A much better thing to do is to actually find the business user. If you've been given a program to add functionality to or to fix something that's wrong, go to the people inside that program or the clients of that business that use that program and say, hi, tell me how you use this thing. And you sit down, shut up, and watch and see how they're actually using it, what they do, how do they actually do their job. Because at the end of the day, the reason this program was made was to solve a problem for an actual user. And if you watch that user using your problem or using your program, you can learn so much so fast, it would take you days to figure out going through the program. But to go back to this, you want to put a breakpoint into where this dictionary is being used. You stop it the first time that that dictionary gets hit to do something. Usually it's where it's going to get populated. So you can literally watch one entry at a time be put into the dictionary. And you can look and see what kind of values and keys are being put in there. And it gives you tremendous insight into what this program is going to do. And it'll give you really good insight into later on, if something's broken, you can look back and go, oh, well, that key value pair, it's empty right here. How could that be empty? Well, let's go back to where we first populated it and see, was there something wrong with entering into the dictionary? Now, these are some specific examples, but it's just to illustrate the thinking process behind how this works. You're always thinking that there's going to be a flowchart, path of execution the program goes through, and there's always going to be declaration of variables, logic, and an end to when things are done. And you're thinking with breaking off chunks of operations, either for building them or analyzing how they work or modifying them after they've been built. It's these tiny, tiny chunks. Good. All right. So let's say you're doing all this, and along the way, you don't know much about how the specific kind of dictionary you find works. There's about, 40 or 50 types of dictionaries, for example, that are now baked in to C#. And they're really valuable. Each of them has a very specialized purpose where it isn't just a generic key value pair, it's that they've also written a bunch of code that optimizes its use of that dictionary for very specific things. For example, you can have a dictionary of authorized users on a website. And the kind of things you're going to want to do with that list are a little bit different than if you have a list of products. On products, you're not going to do things like assign permissions to the users or assign employee IDs to the users or whatever. Over on products, you can do things you wouldn't care about over here, like assign price values or modify or tie it to a sales order or whatever you're going to do, okay? So they built many, many different types of dictionaries. So you get on the job the first day and you, okay, good. Look at what Erik was thinking with, and I kind of broke in and I could see that we're dealing with some sort of an in-memory set of data here, right? It's a dictionary. I don't know what the heck it is. What do you do? What do you do? Where do you go to find out? Now, there's a joke in this industry that we get paid to Google things. More properly, we usually get paid to Stack Overflow things. Stack Overflow is an incredibly valuable website. It's also can be very, very challenging to navigate and just take some time using it. But there are hundreds of thousands of software developers around the world who post issues that they encounter, and they get answers to those issues on Stack Overflow. Another neat thing about being in this industry is you're never really actually alone. There's a worldwide body of geeks. And it's a worldwide body of software developers that love sharing knowledge and love showing an interesting way they solve the problem. And they love, for the most part, helping the newbie out and getting him the data he needs to be able to operate well. So, yes, we get paid to Google for a living, or Stack Overflow for a living, or .NET Pearls, which is a wonderful site, by the way. D-O-T-N-E-T-P-E-R-L-S. .NET Perls is fantastic. He usually has incredibly good, simple, clear examples of how to actually use the command that you're studying, right? The one that isn't a lot of fun, I'm just going to be honest, Microsoft Developer Network, MSDN. You'll find all the actual documentation for everything about that thing there, but very, very few examples of how to actually do it with real-world variable names and real-world implementation. Makes it a lot less useful as a tool. Good. So the point I'm making is you're going to have to figure it out along the way a lot in this industry. It's challenging, yeah, but that's why you get paid a lot. You get paid a lot not because you know a lot going in. Like I told you, on each project I do, I know about 15-20% of the technologies that are being used. When I say know them, I mean know them well, right? But the other 75-80% are things that either I kind of know just got developed in the last 3 or 4 years and I haven't had a chance to mess around with, or, wow, I actually don't even know what that is yet. But I do, and you guys will too, because what you'll know about them without knowing specifically how they're implemented, you'll know that no matter what, they'll have classes, and those classes will have methods, and those methods will take arguments, and those methods will have return things, if they're going to return something, and there you go. That's all it's going to be. It's going to be some newfangled way of arranging, making a new class that can do new methods, new functionality that helps you a lot. Have you actually used it yet? No. But you know that that's what it'll be. It'll be classes, and inside those classes they define methods or types of behavior, and you'll be able to research how to use them. And you're going to have to do the research. So we have this balance here, what we're trying to achieve at the school. And the balance is giving you enough of the fundamental data of how just computers in general work and think, and of how the syntax and structure of the language you are taught works. Balancing that with a very clear, like, here's the exact data. Drill it. Okay, good. Here's some more data. Drill it. Very, spoon-fed is the wrong word. It's not what I'm trying to say. It's given to you in a very easily assimilable form. We're trying to balance that with the fact that the world isn't like that. Your job isn't going to be like that when you get out. This isn't to scare you from the job. It's a lot of fun. And again, because that's the way it is for everybody, even the senior guys, it's not like it's going to be a problem when you get out there. They all know that this is how you figure stuff out. So that balance of spoon-fed the data and really like, okay, good, let's totally assimilate all these basics versus here's something to solve that either we intentionally give you or just comes up along the way because there's so many interconnected pieces, parts in this industry. What do you do when you hit that? Do you stop? You go, oh, darn, I don't know what to do. Where you go? I'm not going to be stopped. Well, is there an error message it's giving me? All right, I got to figure that out. Or I was doing this and it worked well. Let me look that up on the internet. Oh, wow. So yeah, that's how I'm doing that. Oh, look, it says the next thing to do is blank. Oh, because you'll have to do that all the time on the job. You have to go all the time. And by the way, this is not offering up some excuse for not providing really good curriculum. This is actually part of why we're adding what I'm doing right now to the curriculum, so that you'll actually be able to think with this, because this is what will actually happen on the job. But the beautiful thing is that once you learn to think that way, and you know that that's a given part of how your job works, you become very, very able and very powerful, because you know that nothing needs to scare you. None of it. None of it needs to scare you. I actually operated for a long time that way, where like, I've got to know everything. I've got to know everything. That was my own internal junk. You don't need to know everything. What you need to be able to do is figure out anything. And if you can figure out anything, then you're done. And you've got it made, and you'll make a lot of money, and you'll be quite happy. It's a lot of fun to solve these things. It's a lot. How many of you have had the experience where something was not quite working right, and then you finally hit run, and bang, went all the way through? Feels great, doesn't it? It feels great. It feels really great. It's a matter of personal discipline and stick-to-itiveness when you hit those points where it's not working, to just push through. Now that said, we're providing a service here, and this is an educational area, so when you hit one of those things, don't grind for too long. Don't bang your head against it for an hour, hour and a half and go, ugh! Because it's that balance of, yeah, you know at the end of the day that it's up to you to figure it out, but it's also up to your fellow team members to help you. That's what the best environments I've worked in have been like. They are a team, and they're perfectly happy to help. And by the way, if you go out there and you get a job and they're not that way, get out as soon as you can. It's the exception rather than the rule. In this industry, because it's so true that no one will ever know all of it, they're very open to helping. Good. Okay. Now, another couple notes here. Write comments in your code. Document your code. I recommend erring on the side of excess verbosity. A lot more code than you need, comments than you need at the beginning, for two reasons. One is that when you get on the job, they'll like that. They'll like that you're documenting your code. And if you ever get feedback from someone, a little bit too much documentation, that's a fine bit of feedback to get from somebody. But the biggest reason why is that it'll help you while you're learning. It'll help you while you're learning. So, to go back to this drill, for example, that I've mentioned several times in this talk, because it's one that we've just been working on recently. So that example of the file copy, that's really not very good. You have these individual steps, basically, of locate a folder, find all files in the folder, check age of files, copy newer files to the destination. These, as you're developing, as you're writing the code for this, can be broken down into tiny little chunks. Here's a little teeny code snippet. I hope you guys have heard that word. A snippet is just a tiny section of something. And apparently I can't spell it. So you write this tiny little code snippet that can locate a folder. Then you write a tiny little one that can find the files in the folder. And then you actually write another one that can add those to a list. Okay, good, awesome. Then you write a tiny little snippet that will check the age of a file. Then you make it so it can check all the files in a list. And you can give it this list that you made. And then you write a tiny little snippet that will copy a file to a destination folder. And then you write another one that'll copy all the files in the list over to the destination. Little bit by bit by bit, you're putting the whole thing together. If every step along the way you put little teeny notes on each one, locates folder, finds names of all files in folder, checks the age of a single file, checks the age of all files in the list that's passed in, it'll help you tremendously as you're trying to build it. Tremendously. Because you're dealing with, and this is one of the biggest challenges about learning this, I want you to keep this in mind, you're dealing with a lot of significance and very little mass. What do I mean by that? Let's say you're studying a car. The mass of the car is the car. You walk up and you put your hands on the car. Okay, good. And there's a steering wheel and you're touching everything about the car. The significance is the theory or the how-to, the how does it work about a car. That's where your dad tells you when you step on the brake really hard, the tires will skid. So some theory, some significance. Make sense?
Yep.
We're dealing with computers. How big is the central processing unit?
22 nanometers?
Yeah. A little tiny thing, right? And even when you're writing code, if age greater than 18, print, approved, this thing that says age, there's a lot of significance there. It signifies a variable, but it doesn't just signify a variable, it signifies actually the value of that variable. There's so much of this going on when you write your code. Having some nice little English comments that say checks for underage is incredibly valuable. Make sense?
Mm-hmm.
Okay, good. So it's always easier to strip comments out as you realize they're not needed. There are various schools of thought about this. There are people that say that the way you write the code should imply its function so clearly that you don't need comments. True, especially if you're an experienced developer. You can look at it and figure out what it's going to do. I don't agree with that. There's nothing wrong with a good comment. And besides, with the cost of memory nowadays, you're not wasting any of your computer's memory by typing in a few extra lines. Good. All right. So another note on this. What do developers spend their time doing? And by the way, you'll get asked this on some interview questions. Roughly how much time during a given 8-hour day do you expect a coder, a software developer, to be actually writing code? Typical answer is about 2.5 hours. 30%-ish. Okay? Actually writing the code. So what are you doing the rest of the time? Well, the value of that flowchart thing cannot be underestimated. If you do that properly, you've identified every single task that you need to do as a developer. You've identified everything you need to build. And along the way, you've discovered that if you have this step here executed before this step, you break the system. And you've adjusted accordingly. There's no way to replace the value of that process done properly. There's that proper planning prevents poor results, right? And it's true in this industry. So you'll spend a lot of your time actually figuring out the functionality ahead of time before you write any code. What else do you spend your time doing? Well, there's that whole what's wrong and where do I go to figure it out? And then there's the getting advice from a friend, fellow developer, on the right approach to solving a certain thing. And then there's, you worked for 2 weeks and got a bunch of stuff done, stop, take stock of how well did this go, and change your mode of operating basis from here forward. Really, really valuable stuff. So, at the end of the day, you're going to spend about 30% of your time actually writing the code. The effectiveness of how well you write it is totally reflected in how do you spend the other 5.5 hours a day. All right? All right, I think I've covered a lot of this stuff here. The last thing is stable data that apply to programming regardless of language. And we covered the fact that a program really just essentially has a few key elements. It's got to declare variables, it's got to have some logic that gets applied, and it's got to end. But the thing that all programs really have, all programming languages have in common is really algorithms. A series of steps that get a finite, very well-defined result. They don't go on to infinity. They're not vague or ambiguous on the steps. Algorithms are everything. They really are. If, boom, you're now into algorithm territory. For each, you're in algorithm territory. So, if I recommend any one thing to really concentrate on, in your own like off time or drilling or whatever, or go back and just look at it again, it's all the different ways you can actually apply an algorithm occurring and get very, very comfortable with them. Because essentially, all you're doing is you have a bunch of, you're defining an object, and it has in it properties, and it has fields in it, correction, and it has methods. This is what's it like, and this is what can it do. And this object, you're going to be able to scan through all the different elements in it. You want to be able to do that. How do you do that? How do you iterate or jump through or add to or take away from. This is algorithms. So make this your friend. Make the study of these things your friend. At the end of the day, if you get thrown a new language, the core elements you're going to instantly learn is how to make an algorithm work. The other extraneous stuff about peculiarities of that language and how it accesses databases and how to throw data up on a computer screen or how it renders a web page or whatever, you can learn that. And that's not going to restrict your ability, but if you can't write an algorithm to grab a data set, parse through it, find the exact piece of data you want, change it, and insert it back in, you're toast. This is one where it's an interesting balance. It's not a delicate balance. It's a very simple, clear-cut balance. And it's the kind of thing I was talking about before. And that's a good question. We are trying here to create an environment for learning where we replicate as well as we can the environment you actually can operate in, with a couple very minor exceptions. The environment you'll operate in, if you don't know about programming, will be horrifically confusing and frustrating, because there is this baseline level of data. But once you have that baseline level of data, frankly, if you've been on the job 6 months or a year, you're all in that big lump of, I've got some experience as a developer. The environment is the same, whether you've been in for a year and a half or 20, and it's the thing I was talking about before, where you just kind of have to figure it out as you go along. What we're trying to do is short-circuit that 6 months to a year of being on the job, and there are going to be times where the things that we're putting together for you don't work, where there's a drill, and you're going through it, and like, it didn't come out the way you wanted it to. Now I'm going to level with you. That can be very frustrating. That can be very frustrating. 20 years down the line of having done development, it can be very frustrating when it happens to me. So I completely understand. And again, it did just happen this morning. And I won't go into a bunch of the geeky details on what occurred, but we're building a very large, complicated system. And there's 5 different developers working on it all at the same time, any one of them could put some new code in that breaks what you've got working. And you have to reconfigure a bunch of stuff. And that happened like 3 different times today. And none of us are really sure what broke it. Fun. Not really fun. But you have to figure it out, right? So the approach I recommend in terms of like keeping your sanity is to define for yourself that point where if you go past it, you know you're just going to lose it. And up until you hit that point, just try to solve it yourself or with the help. And by that I mean the help of the texts or the videos you've watched or what you can find on Google or even grabbing an instructor, right? But I recommend seeing how much of that you can figure out and how far out you can put that threshold. Not as a like, I'm a glutton for punishment and great, I just spent 3 days grinding on how to operate the print function in Python 2.7 versus 3.4, right? But that grind isn't really, it's more of an indication of like your willingness to do what's really going to be needed when you get on the job. That said, don't put it too far out. That's why we're here. We're here to make it so that it doesn't end up being something you take a lose at. But we're also not here to solve it the second you encounter it, because then we bypass that incredibly valuable process. And that there's nothing like it. There's nothing like, I don't know how to solve this. And then you get it. There's just nothing like that. And the beautiful part is you get to turn around and tell someone else, oh, when you hit that, here's what you do. That, by the way, is what stack exchange is. That's all it is. Somebody else encountered the exact same thing and they're like, oh, cool. Everybody ought to know about this. Bam. And there it is up there, right? So I guess that's what I want to say about that.